perceive as smooth, continuous, and solid. The fabric of the biggest puzzle in physics today.
Yeah, absolutely. Because we have these two amazing theories, right? General relativity for the big stuff.
Right. Galaxies, black holes, the whole cosmos.
Yeah.
Works beautifully.
The really extreme places, like the very beginning of the Big Bang, or smack in the middle of a black hole.
You just get infinities. Things that make no sense.
Exactly. Nonsense answers. It's like the theories they just can't talk to each other at those points.
So that's our mission for this deep dive. We're going to explore this, well, pretty radical idea that maybe the universe isn't smooth at all. That it's actually granular, pixelated, governed by something called the Planck-Scale.
And how looking at it that way might actually fix some of these huge problems.
Yeah, how this pixelated view could resolve the paradoxes and give us a whole new picture of reality. It's pretty wild stuff.
It is.
So let's start right there. This term Planck-Scale. What is it exactly? Where does it come from?
Okay, so the Planck scale, it goes back to Max Planck, actually, way back in 1899. He realized you could take the fundamental constants of nature.
The really basic ones.
The most basic. The speed of light, C. Newton's gravitational constant, G, and the Planck constant, which governs quantum effects. And just by combining those three in different ways, you can come up with units for length, time, mass, energy that are completely universal.
Universal hat.
Meaning they don't depend on, human conventions like meters or seconds. Any intelligent being anywhere in the universe, if they discover these same fundamental laws, they'd arrive at the exact same values.
Ah, okay. That's why some people call them God's units. Sort of jokingly.
Sort of jokingly, yeah. Because they're built into the fabric of reality itself. Now, the scales involved are, well, they're extreme. The Planck length. It's about 1.6 times 10 to the minus 35 meters.
Okay, hold on. 10 to the minus 35. How small is that?
It's unimaginably small. Think about a proton. Tiny, right?
Yeah.
A proton is about 10 to the 20 times bigger than the Planck length. 100 billion times bigger.
Wow, okay. Almost impossible to picture.
And the Planck time. That's the time it takes light to cross one Planck length. That's 10 to the minus 44 seconds. Our physics basically stops before that point after the Big Bang.
So minuscule length, minuscule time. What about the energy?
Now that's the counterintuitive part. The Planck energy is huge. It's about 2 billion joules.
2 billion. That sounds macroscopic.
It is. It's roughly the energy in a full tank of gas for a car. So tiny, tiny lengths and times, but enormous energy packed into that scale.
Why is that scale so important then? Why does this specific combination of tiny and huge matter so much?
Because it's the point where everything collides. It's where quantum effects, the weirdness of the small, become just as strong as gravity, the warping of space-time.
Two pillars.
They meet right there, and our separate theories for them just break. You can't ignore quantum effects when talking about gravity at that scale, and you can't ignore gravity when talking about quantum fields at that energy. You absolutely need a theory of quantum gravity.
Okay, but if it's that small, 10 to the minus 35 meters, how can we possibly know that's a real limit? We can't build a ruler that small, right? Is it just theoretical, or is it physically impossible to go smaller?
That's a great question, and the answer seems to be it's physically impossible, not just a limit of our technology, but a limit imposed by nature itself. And the way we deduce this is through a really clever thought experiment, sometimes called the black hole microscope.
A black hole microscope. How does that work?
Well, think about how you try to see something really small. Quantum mechanics tells you need a probe with a very short wavelength, right?
Yeah, like using electrons instead of light in a microscope to see smaller things. Shorter wavelength, better resolution.
Exactly. And shorter wavelength means higher energy. So to see something as small as the Planck length, you'd need a probe with enormous energy approaching the Planck energy.
Okay, that massive energy we talked about.
Right. Now, bring in Einstein. EMC squared tells us that huge energy means huge mass, effectively.
Energy and mass are two sides of the same coin.
Got it. And then general relativity steps in. It tells us if you cram enough mass or energy into a small enough space,
you get a black hole.
You get a black hole. So here's the paradox. If you try to create a probe energetic enough to measure something smaller than the Planck length, you concentrate so much energy in such a tiny region that you inevitably
create a black hole that swallows up whatever you were trying to measure.
Precisely. And if you try to use even more energy to get better resolution, you just make a bigger black hole, hiding even more.
Whoa. So nature itself prevents us from seeing beyond that point.
It seems so. The very act of measuring creates an event horizon that blocks your view. It suggests the Planck length isn't just small, it's the smallest meaningful distance. Like the universe has a fundamental resolution limit.
Almost like pixels on a screen. You can't see detail smaller than 1 pixel.
That's a really good analogy. And it connects to ideas like black hole entropy, where the information seems related to the surface area, not the volume, suggesting information is stored in these Planck-sized bits on the boundary.
Okay, that's a powerful thought experiment.
Yeah.
How is this idea captured mathematically? Is there like an equation for this limit?
There is, actually. It's called the generalized uncertainty principle, or GUP.
Like Heisenberg's uncertainty principle.
Exactly, but generalized. Heisenberg said you can't know both position and momentum perfectly. The more you know one, the less you know the other.
Right. Delta x times delta p.
Is greater than or equal to h bar over 2. Yeah. The GUP adds an extra term to that inequality, a term related to gravity.
Okay, what does that extra term do?
Well, its effect is negligible usually. But when you get to really high energies, really high momentum uncertainties, exactly what you need to probe tiny distances, this extra term kicks in. And it means that your uncertainty in position doesn't go down to 0 as your momentum uncertainty goes up. Instead, there's a minimum possible uncertainty in position.
A floor. You can't get more precise than a certain amount.
Exactly. And that minimum position uncertainty, it turns out to be right around the Planck length.
So the math itself, this GUP, backs up the black hole microscope idea.
It does. It formalizes it. And it suggests this isn't just about space, but time too. Both space and time are fundamentally granular, not continuous. And what's really compelling is that this GUP idea pops up in lots of different approaches to quantum gravity. It seems quite robust.
Wow. Okay, so if space-time isn't smooth, if it has this fundamental graininess, this minimum length, what does it actually look like down there? What's the picture?
The picture that emerges is often called space-time foam. It's a term coined by the physicist John Wheeler.
Space-time foam. Like bubbles.
Sort of, yeah. Think about it. If space-time is fundamentally discrete, then the smooth, continuous geometry of Einstein's theory is just an approximation, something we see at low energies, like looking at water from far away.
Okay.
But zoom in to the Planck scale, and it's not smooth at all. Wheeler envisioned it as a wildly fluctuating, chaotic place. Quantum uncertainty applied to geometry itself.
So distances and times aren't fixed down there.
They lose their definite meaning. The geometry is constantly churning. You might even have tiny virtual black holes popping in and out of existence in a fraction of a second at Planck time.
Virtual black holes.
Seriously. That's the idea. A sea of quantum fluctuations so energetic they can warp spacetime into these tiny, fleeting configurations. It's the ultimate expression of a granular universe, a dynamic, foamy quantum substrate underlying the smooth reality we perceive.
Okay, that's a mind-bending image. But it brings up a huge question. If space-time has this granular structure, maybe like a grid or lattice at the bottom, doesn't that violate one of the absolute cornerstones of physics? Lorentz invariance.
Ah, yes, the big one. You've hit on a major, major challenge. The discreteness versus Lorentz invariance dilemma.
Because Lorentz invariance says the laws of physics look the same no matter how fast you're moving, right?
Yeah.
No preferred direction or speed.
Exactly. It's the bedrock of special relativity. It's a continuous symmetry. But if you imagine space-time as, say, a fixed, rigid grid of points.
Like a checkerboard.
Yeah. Then someone moving relative to that checkerboard would see the distances between points differently, wouldn't they? They'd measure different fundamental lengths or times depending on their motion relative to the grid.
Which would violate Lorentz invariance. You'd have a preferred frame, the frame of the grid itself.
Precisely. So how do you reconcile a fundamental length, the Planck length, with the principle that there's no preferred frame? It's a deep conflict.
So how do physicists try to solve this? What are the options?
Well, there are a few main lines of thought. One possibility is maybe Lorentz invariance isn't perfectly exact.
Sacrilege. But, yeah. Okay. What would that mean?
It might mean that the speed of light isn't perfectly constant, but could depend very slightly on the energy of the light particle, the photon.
So high-energy light might travel at a slightly different speed than low-energy light.
Exactly. Just an incredibly tiny difference, only noticeable at extreme Planck-scale energies. But, and this is the cool part, maybe we could detect it.
Wow.
By looking at things like gamma-ray bursts coming from billions of light years away. If high-energy gamma rays travel just a tiny bit faster or slower than lower-energy ones over those vast distances, the difference in arrival time could add up enough for us to potentially measure it.
Wow. So we could actually test for violations of Lorentz invariance.
People are looking. So far, no definitive detection, which puts tight constraints on these models, but it's an active area of research.
Okay, what's another approach? One that maybe doesn't break Lorentz invariance?
Another idea is called doubly special relativity, or DSR. It's clever. It says, okay, the speed of light e is invariant for everyone, like Einstein said. But what if the Planck energy, EP, is also an invariant constant for all observers?
Wait, two invariant scales. How does that help?
It modifies the rules of how energy, momentum, and velocity transform between different observers, the Lorentz transformations, in such a way that no one can ever measure a length shorter than the Planck length or an energy higher than the Planck energy. Lorentz contraction still happens, but it sort of maxes out near the Planck scale.
So it preserves a minimum length and Lorentz invariance, but by changing the transformation rules.
Essentially, yes. It's a mathematically consistent way to have both.
Okay, that's elegant. Any other ideas? Maybe more radical ones?
The most radical, perhaps, comes from theories like loop quantum gravity and causal set theory. They suggest Lorentz invariance isn't fundamental at all.
It emerges.
Exactly. It emerges only at large scales, in the low-energy world we experience. In these theories, the fundamental structure isn't a fixed grid or background. Space-time itself is built from relationships, quantum connections, or causal links between events.
So there is no background grid to move relative to.
Right. If space-time is fundamentally relational and dynamic, there's no absolute background and thus no preferred frame to violate Lorentz invariance in the first place. It sidesteps the problem entirely.
That's a deep philosophical shift, isn't it? Is space-time a thing, a container, or is it just the network of relationships between events?
That's precisely the debate. Substantivalism versus relationalism. It's a fundamental question these theories are grappling with.
Fascinating. Now, you mentioned earlier how these discrete ideas might solve the infinity problems in quantum physics. Can we unpack that a bit more? Quantum field theory, infinity's renormalization.
Right. So quantum field theory, or QFT, is our incredibly successful framework for describing particles and forces. But it assumes space-time is a smooth continuum, right down to zero distance. And when you do calculations in QFT, especially involving interactions at very short distances or very high energies, you often run into mathematical infinities. The equations just blow up.
Which isn't physically realistic.
Not at all. For decades, physicists have used a technique called renormalization to handle these infinities. It's kind of a sophisticated way of subtracting out the infinite parts to get finite, measurable predictions. And it works astonishingly well.
So well that some people call it a mathematical trick.
Some do, yeah. It feels a bit like sweeping the problem under the rug, even though it gives the right answers. But if space-time isn't continuous, if it has a fundamental granularity at the Planck scale,
then the problem goes away.
It provides a natural solution. If there's a minimum distance, the Planck length, then those calculations never actually reach zero distance or infinite energy. There's a built-in cutoff.
The integrals just stop.
They stop at the Planck scale. The infinities never appear in the first place. Calculations become naturally finite.
So renormalization isn't just a trick, it's actually a hint about the universe's true, discrete structure.
That's the perspective this offers, yes. It suggests the universe at its core might be more like, well, like a giant computation with a maximum resolution, rather than a perfectly smooth geometric object. The infinities were just artifacts of assuming smoothness where it didn't exist.
That connects to something else you mentioned, causal set theory. How does this granular view change our understanding of causality itself?
It potentially flips it on its head. In standard physics with continuous spacetime, causality comes from the geometry. Light cones define what can affect what. Time is like a dimension you move along.
A causes B if B is in A's future light cone.
Right. But in a fundamentally discrete picture, especially like causal set theory, maybe causality is the primary thing.
More fundamental than space or time.
Exactly. In causal set theory, the universe is just a growing collection of discrete events. The only fundamental structure is the causal relationship. Event A precedes event B. Written A, E, B.
So spacetime itself is just this web of causal links.
That's the idea. Spacetime emerges from this network of A caused B. Time isn't a dimension. It's the actual process of new events being generated, adding to the causal set. The universe literally grows, one event at a time.
Wow. That's profound. So the laws of physics are?
They become rules, like algorithms, that govern how new events are created and linked to previous ones. It really pushes this view of the universe as a kind of ongoing computation, where information flows strictly according to these causal links.
Okay, let's make this more concrete. How do these ideas, discrete space, atoms of geometry, causal links, actually get turned into working theories? You mentioned loop quantum gravity.
Right. Loop quantum gravity, or LQG, is a major player. It tries to directly quantize Einstein's general relativity without assuming a background spacetime.
Background independence, that was key.
Absolutely central. LQG asks, what are the quantum states of spacetime itself? It reformulates Einstein's equations using special variables, Ashtekar variables, that make them more amenable to quantum rules.
And what picture emerges?
The picture is that quantum states of space are represented by these things called spin networks. Think of them as abstract graphs.
Like Tinker Toys.
A bit like that, yeah. The links or edges in the graph represent elementary quanta of area. They carry labels, spins, that determine their area. And where the links meet, at the nodes or vertices, these represent elementary quanta of volume.
So space itself is made of discrete chunks of area and volume.
At the quantum level, yes. Our perception of smooth, continuous space emerges from an incredibly dense and complex weave of these spin networks, like how a smooth fabric is really woven from tiny threads.
And a key prediction is?
The quantization of geometry. If you define operators for measuring area or volume in LQG, they have discrete spectra. They can only give certain values, like energy levels in an atom. There's the smallest possible non-zero area related to the Planck area.
So any surface, like a black hole horizon, is literally made of a finite number of these area atoms.
That's the prediction. And the evolution of these states, how geometry changes, is described by spin foams, which are like histories or paths of spin networks through time.
That's a very geometric picture. What about the other approach you mentioned, causal set theory? How does that differ?
Causal set theory, or CST, takes a more minimalist, almost austere approach. Its mantra is order plus number geometry.
Order plus number.
Yeah, the order is causality. The fundamental thing is just a set of discrete events with a partial order relation. A precedes B, that's the bedrock.
And the number.
That's discreteness. The idea is that if you take any finite chunk of space-time, the number of fundamental events within it is finite and roughly proportional to the space-time volume measured in Planck units.
So just two axioms.
Yeah.
Causal order and fundamental discreteness.
That's it. Everything else, the smooth space-time manifold of general relativity, our notions of distance, time, dimension, is supposed to emerge as an approximation when you have a huge number of these events.
And it handles Lorentz invariance well.
That's one of its strengths, because the foundation is purely relational, just the order of events. There's no built-in grid, so Lorentz invariance naturally emerges in the large-scale limit. It's quite elegant.
So putting these together, LQG focuses on quantizing geometry, CST focuses on causal order. How do they stack up against something like string theory? What's the big picture?
Well, the biggest divide, as we touched on, is background independence. LQG and CST are background independent. They build space-time. String theory, traditionally, is background dependent. It studies strings vibrating in a pre-existing space-time.
Which feels less fundamental if you take general relativity seriously.
That's often seen as string theory's biggest conceptual weakness. But its great practical strength has been its connection to quantum field theory, allowing for powerful calculations like getting black hole entropy right.
Whereas LQG and CST,
they have arguably more conceptual purity regarding gravity, but they face huge challenges in actually calculating things and making testable predictions. Getting the smooth space-time we see to emerge dynamically from spin networks or causal sets is incredibly hard.
So it's a trade-off between conceptual foundations and calculational power right now.
Largely, yes. And within the background independent camp, you have this split. Is quantum geometry, LQG, or quantum causality, CST, the more fundamental starting point? It's a very active, very challenging research landscape.
Let's pivot to the consequences. If these ideas are right, what happens at the Big Bang? You mentioned a big bounce.
Right. The classical Big Bang starts from a singularity, infinite density, infinite temperature. Physics breaks. But loop quantum cosmology, LQC, applying LQG ideas to the whole universe changes that.
Right.
As the universe contracts down towards the Planck density, the quantum geometry effects become dominant. They create a kind of repulsive force, a quantum pressure that wasn't there in classical physics.
So gravity becomes repulsive at extreme densities.
Effectively, yes. This quantum repulsion overwhelms the classical attraction, halts the collapse, and causes the universe to bounce.
So no singularity, just a transition from a previous contracting phase to our current expanding one.
Exactly. A smooth big bounce replaces the singular Big Bang. And this isn't something you have to put in by hand. It's a generic prediction of LQC.
Does this connect to inflation, the rapid expansion phase just after the Big Bang?
It does, quite beautifully. Getting inflation started usually requires some fine-tuned initial conditions. LQC might provide those naturally. The physics before the bounce can set up the conditions after the bounce perfectly for inflation to occur.
Making inflation almost inevitable.
That's the suggestion. It makes inflation a natural consequence of the quantum bounce dynamics.
Could we ever see evidence of this bounce?
Possibly. The extreme physics around the bounce could have left subtle imprints on the fluctuations in the very early universe, the seeds of galaxies.
Which we see in the cosmic microwave background.
Precisely. We might look for specific patterns in the CMB, like suppressed power at the largest scales, or particular types of non-Gaussianity that could be relics of the bounce era, a faint message from before the expansion began.
Incredible. Okay, if singularities are resolved at the Big Bang, what about inside black holes? Do they bounce too?
The logic is very similar. LQG predicts that the singularity at the center of a classical black hole is also replaced by a region of finite Planck-Scale density. Infinite compression is forbidden.
So what's there instead?
One compelling model is the Planck star. As matter collapses, it hits this Planck density limit, the quantum pressure pushes back, and it bounces.
But wait, if it bounces, why do black holes seem so stable? Why don't they just explode immediately?
Time dilation. This is the crucial insight from Carlo Rovelli and Francesca Vidotto. From the perspective of the collapsing matter, the bounce is incredibly quick microseconds.
Okay.
But for us, watching from far away outside the black hole, the intense gravity causes extreme time dilation. That microseconds-long bounce gets stretched out.
Over billions or trillions of years.
Exactly. Over a timescale comparable to the black hole's eventual evaporation time via Hawking radiation.
Oh.
So what we see as a black hole is actually this Planck star, collapsing and bouncing in incredibly slow motion.
That's amazing. And what about the information paradox? Does information still get lost?
This potentially solves it. Because there's no singularity, information isn't destroyed. It's stored within the Planck star, effectively frozen by time dilation.
And when the black hole evaporates?
As it shrinks, the time dilation weakens. Eventually, the bounce can complete, the Planck star effectively becomes a white hole, and it releases the stored information back out.
Could we detect that explosion?
Maybe. It could produce a burst of very high-energy particles, perhaps detectable gamma rays, though likely with very specific characteristics. It's another potential observational window.
So the big bounce and the Planck star bounce?
Mm-hmm.
They're the same fundamental physics.
Conceptually, yes. A universal quantum gravity effect that resolves classical singularities through a bounce, driven by the fundamental granularity of space-time. It turns these endpoints into transition points.
Okay, bringing it all together. How does this granular picture mesh with the holographic principle, that idea that information is related to surface area?
It actually provides a microscopic explanation for it, especially in LQG. Remember, the holographic principle came from black hole thermodynamics entropy proportional to area.
Right, which seemed weird if space has volume.
But in LQG, when you calculate the black hole entropy, you do it by counting the number of spin network links, the quanta of area that puncture the 2D event horizon surface.
So you're literally counting surface degrees of freedom.
Exactly. And the calculation naturally gives an entropy proportional to the area, matching the Bekenstein-Hawking formula. It derives holography from the underlying quantum geometry.
So holography isn't just some weird principle imposed from above. It's an emergent property of the granular spacetime.
That's the interpretation, yes. It suggests a deep consistency between the discrete structure and the way information is encoded in gravity. CST also shows hints of holographic behavior.
It feels like a very coherent picture is emerging. But what are the big roadblocks? What are the main things researchers are struggling with right now?
Oh, there are definitely major challenges. One is the problem of dynamics in LQG. We have a good handle on the possible states of quantum space, kinematics, but the rules for how they evolve dynamics, particularly implementing the Hamiltonian constraint from GR, are really tough.
Getting the movie from the snapshots.
Kind of, yeah. Another huge one is the semi-classical limit. How do you rigorously show that the smooth, classical spacetime of Einstein's theory definitely emerges from this discrete quantum structure at large scales? That's still an open problem.
Showing the theory recovers the reality we actually observe.
Crucial. And then there's coupling to matter. How do you incorporate all the particles of the standard model, electrons, quarks, photons, into these fundamentally background-independent geometric frameworks? It's very complex.
And finally, the big one, testable predictions.
Always the toughest part for quantum gravity. We have potential candidates, CMB signatures, gamma ray signals from bouncing black holes, tiny Lorentz violations, but refining these into sharp, unambiguous predictions that experiments can target is the ultimate goal, and there's still a way to go.
So, stepping back from the details, what's the big takeaway message from this whole exploration of a pixelated cosmos?
I think the core message is that thinking about the universe as fundamentally discrete, limited by the Planck scale, seems to offer a surprisingly unified way to tackle the deepest conflicts between our best theories of gravity and quantum mechanics.
It resolves paradoxes like singularities and information loss.
It replaces them with concrete physical processes like quantum bounces. It suggests a paradigm shift away from continuous geometry towards a reality built from discrete quantum information and causal relationships.
A different foundation for reality.
A fundamentally different foundation. And while no single theory has all the answers yet, the final picture might involve a synthesis, maybe combining the background independence of LQG or CST with insights and tools from string theory, particularly around holography.
The Planck scale is like a guidepost.
It really is. It's this universal boundary telling us where current physics breaks down and where the new fundamental laws must lie. It's guiding the search.
We've certainly covered some mind-bending territory, from space-time pixels to a big bounce instead of a big bang, to black holes that store information and eventually pop. It's a radical rethinking.
It absolutely is.
And it really leaves you wondering if space-time is fundamentally granular, and if information, these causal links, are what truly define it. Could the universe itself be seen in some deep way as a kind of giant, unfolding cosmic computation?
That's one of the most profound implications, isn't it?
Where the laws of physics we observe are just, the algorithm running the simulation? Something to chew on, definitely.
A lot to think about.
Well, keep pondering these amazing questions, and join us next time for another deep dive into the universe's mysteries.